Namaskar, I welcome all of you to my YouTube channel. This is lecture number 31 on complex analysis, and today's topic of discussion is Cauchy's residue theorem. First, let me read the statement. According to Cauchy's residue theorem, if a function f of z is analytic within and on a closed curve C except at a finite number of poles within C, then integration along closed curve C f of z dz is equal to twice pi iota into summation r, where summation r is the sum of residues at the poles within the closed curve C. Now, let us understand what is the meaning of this statement. Students, suppose we have a closed curve C, and within this closed curve C we have finite number of poles where the function f of z is not analytic. However, except these poles, this function f of z is analytic at all points within and on the closed curve C. If this condition is satisfied, then according to Cauchy's residue theorem, integration along closed curve C f of z dz is equal to twice pi iota into residue at the pole z equal to a1 plus residue at the pole z equal to a2 plus residue at the pole z equal to a3 plus dot 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 plus residue at the pole z equal to an. Now, let me write these points. Note number 1. If a1, a2, a3, dot 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 an are the poles within the closed curve C, then according to Cauchy's residue theorem, integration along curve C f of z dz is equal to twice pi iota into residue at z equal to a1 plus residue at z equal to a2 plus residue at z equal to a3 plus dot 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 plus residue at z equal to an, bracket close. Note number 2. If there is no pole within the closed curve C, then integration along closed curve C f of z dz is equal to twice pi iota into 0, that means 0, and this is known as the Cauchy's integral theorem, and this is known as the Cauchy's integral theorem, and I had explained this theorem in lecture number 16. Okay? Now, let us solve some numerical problems to understand Cauchy's residue theorem properly. Problem number 1. According to this problem, we have to evaluate this integral where C is the circle modulus of z equal to 2. Now, let me solve this problem. Given the complex function f of z is equal to sin z divided by twice z minus pi. We know that poles or singular points can be obtained by putting the denominator equal to 0. So, if we do, then we have seen that z equal to pi by 2 is a pole of order 1. Now, let me write these points. Here z equal to pi by 2 is a simple pole, and this simple pole lies inside the given circle whose radius is 2 and the center is at z equal to 0. So, pi by 2 means 1.57. So, this will be the location of the simple pole. So, here z equal to pi by 2 is a simple pole which lies inside the given circle modulus of z equal to 2. Radius of the circle is 2 and center at z equal to 0. Next, let us find out residue at z equal to pi by 2. So, residue at z equal to pi by 2 is given by limit z tends to pi by 2 z minus pi by 2 into f of z. Here f of z is sin z divided by twice z minus pi. Next, let us take common 2 from the denominator of this term. So, we will get 1 by 2 limit z tends to pi by 2 z minus pi by 2 into sin z divided by, if we take common 2 from the denominator of this term, then we will get z minus pi by 2. Z minus pi by 2 into 1 by z minus pi by 2 will be cancelled out. So, finally, we will get half limit z tends to pi by 2 into sin z. If we substitute the limit, then we will get half into sin pi by 2. We know that sin pi by 2 value is 1. So, finally, we get residue at z equal to pi by 2 as 1 by 2. So, we have seen that residue at z equal to pi by 2 is half. Now, let us apply Cauchy's residue theorem. So, therefore, by Cauchy's residue theorem, integration along closed curve C sin z divided by twice z minus pi into dz is equal to twice pi iota into residue at z equal to pi by 2. Here we have seen residue at z equal to pi by 2 is 1 by 2. Now, let us substitute the value here. So, twice pi iota into 1 by 2. So, after simplifying, we are getting integration along closed curve C sin z divided by twice z minus pi into dz as pi iota. This is the answer. Next, let me solve problem number 2. According to this problem, we have to evaluate this integral where C is the circle modulus of z equal to 1. Now, let me solve this problem. Given the complex function f of z is equal to sin z divided by z to the power 6. Now, let us expand the term sin z. So, finally, we will get 1 by z to the power 6 into z minus z cube divided by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial plus dot dot dot. Next, let us multiply this term with this term. So, finally, we will get 1 by z to the power 5 minus 1 by 3 factorial into 1 by z cube plus 1 by 5 factorial into 1 by z minus z divided by 7 factorial plus dot dot dot. Here we have seen that the principal part contains total 3 terms which is finite. So therefore z equal to 0 is a pole of order 5 because here highest negative power of z is 5. First let me write these points. Here z equal to 0 is a pole of order 5 because highest negative power of z is 5 and the pole at z equal to 0 lies inside the given circle whose radius is 1 and center at z equal to 0. So this is the location of the pole. Also the pole z equal to 0 lies inside the given circle whose radius is 1 and center at z equal to 0. So therefore residue at z equal to 0 is given by coefficient of the term 1 by z minus 0, ultimately 1 by z. So here we have seen that the coefficient of 1 by z is 1 by 5 factorial. 1 by 5 factorial. Now let us apply Cauchy's residue theorem. So therefore by Cauchy's residue theorem, integration along closed curve C sin z divided by z to the power 6 dz is equal to twice pi iota into residue at z equal to 0. We have seen that residue at z equal to 0 is 1 by 5 factorial. So let us substitute the value here. So finally we will get 2 pi iota into 1 by 5 factorial. 1 by 5 factorial is 1 by 120. So finally we will get pi iota divided by 60, which is the answer. Okay. Next let me solve problem number 3. According to this problem we have to evaluate this integral where C is the circle modulus of z minus 1 equal to 1. Solution to problem number 3. Given the complex function f of z is equal to twice z square plus z divided by z square minus 1. Here we have seen that z equal to plus 1 and minus 1 are the simple poles. The location of these poles are at this point and at this point. Again we have seen that only pole at z equal to 1 lies inside the given circle whose radius is 1 and center at z equal to 1. Let me write these points. Here z equal to plus 1 and minus 1 are the simple poles. Simple poles. However, only one pole at z equal to 1 lies inside the given circle. Inside the given circle, modulus of z minus 1 equal to 1. Now let us find out the residue at the pole z equal to 1. So therefore, residue at z equal to 1 is given by limit z tends to 1 z minus 1 into f of z. Here f of z is twice z square plus z divided by z square minus 1. Let us simplify this term. Limit z tends to 1 z minus 1 into twice z square plus z divided by z minus 1 into z plus 1. Here we have seen that z minus 1 and z minus 1 will be cancelled out. So finally we will get limit z tends to 1 twice z square plus z divided by z plus 1. Next, let us put the limit. So after putting the limit, we will get 2 plus 1 divided by 1 plus 1. So we will get 3 by 2. Next, apply Cauchy's residue theorem. So therefore, by Cauchy's residue theorem, we have integration along closed curve C twice z square plus z divided by z square minus 1 into dz is equal to twice pi iota into residue at z equal to 1. Here we have seen that residue at z equal to 1 is 3 by 2. So after substituting, we will get twice pi iota into 3 by 2. So after simplifying, we will get 3 pi iota. This is the answer. Okay. Finally, let me solve problem number 4. According to this problem, we have to evaluate this integral where C is the circle modulus of z equal to 3 by 2. Solution to problem number 4. Given the complex function f of z is equal to 4 minus 3z divided by z into z minus 1 into z minus 2. Here we have seen that z equal to 0, z equal to 1 and z equal to 2 are the simple poles. So these are the location of these simple poles. Again, we have seen that only two poles at z equal to 0 and z equal to 1 lies inside the given circle whose radius is 1.5 and center at z equal to 0. Now let me write these points. Here z equal to 0, 1 and 2 are the simple poles. Simple poles. However, only two poles at z equal to 0 and z equal to 1 lie inside the given circle modulus of z equal to 3 by 2. Now let us find out residue at z equal to 0 and at z equal to 1 separately. So therefore, residue at z equal to 0 is given by limit z tends to 0, z minus 0, that means z into f of z. So f of z is 4 minus 3z divided by z into z minus 1 into z minus 2. This z and this z will be cancelled out. So finally we will get limit z tends to 0, 4 minus 3z divided by z minus 1 into z minus 2. Next, let us put the limit. So after putting the limit, we get 4 minus 0 divided by minus 1 into minus 2. That means 4 by 2. So finally we will get 2. So residue at z equal to 0 is 2. Again, residue at z equal to 1 is given by limit z tends to 1 z minus 1 into f of z. That means 4 minus 3z divided by z into z minus 1 into z minus 2. This z minus 1 and this z minus 1 will be cancelled out. So finally we will get limit z tends to 1, 4 minus 3z divided by z into z minus 2. Again, let us substitute the limit. So finally we get 4 minus 3 equal to 1 divided by 1 into minus 1. So minus 1. So residue at z equal to 1 is minus 1. So we have seen that residue at z equal to 0 is 2 and residue at z equal to 1 is minus 1. Now let us apply Cauchy's residue theorem. So therefore by Cauchy's residue theorem, integration along curve C 4 minus 3z divided by z into z minus 1 into z minus 2 into dz is equal to twice pi iota into residue at z equal to 0 plus residue at z equal to 1. We know residue at z equal to 0 is 2 and residue at z equal to 1 is minus 1 and 2 minus 1 is 1. 1 into twice pi I equal to 2 pi iota, which is the answer. This is all about today's video and I hope that you have learnt a lot from this video.